Good morning, Algebra 2 CP. Today we're going to be talking about graphing linear functions. This should largely be a review from Algebra 1, but it lays a great foundation for functions going forward because we're only going to be doing higher orders of functions in the future in Algebra 2. So to understand linear functions is a really good baseline to build off of. So let's start by defining what a linear function actually is. I'm then going to show you a couple forms of a linear function that you typically see them presented to you in, and then talk to you about how to graph them, show you a couple examples, and we'll be on our way. So before we actually graph a linear function, let's first define what a linear function actually is. And a linear function is a degree 1 function. And again, remember that means that the highest exponent that you see in the function is 1, x to the first. That graphs to a line. And you can see the word line in the name linear as well. So that's a nice little reminder that these all graph to straight lines, not curves, not parabolas, no bumps, just regular old line. Okay? You're probably used to seeing linear functions presented to you in this, what's called slope-intercept form. Or at least that's how most students feel comfortable with graphing lines in slope-intercept form. And slope-intercept forms looks like this: y equals mx plus b. And the reason why it's called slope-intercept form is because it gives you two pieces of information right off the bat: the slope and the y-intercept. M, if you remember, is what we call the slope. And the slope refers to how steep the graph is slanted. You can have a positive slope. A positive slope will rise up and to the right. A negative slope will fall down as you go from left to right. It always goes from left to right, slope does. And slope, you may recall, is defined as rise over run. And now already you might be like, well, Mr. Giorgio, why'd you say rise as R-Y-S-E? Don't you know how to spell? Yes, I do know how to spell. And the reason is because it's a nice little reminder that rise refers to the Y, vertical, right? Rise over run. You can't run straight up a wall. Run is horizontal, rise is vertical, okay? And again, just to draw a little diagram here, any line that slopes up and to the right like that, we would say that has a positive slope, because as you're moving from left to right, you are going uphill. Any line that slopes like this, we would say has a negative slope, because as you're going left to right, just like reading a book, you would be going downhill, correct? And lastly, any horizontal line, we would say has zero slope, right? If you're just perfectly flat, not going anywhere, your slope at that particular point is 0. And again, a nice definition of slope is, again, how steeply a line is inclined. You may also think of it as the rate of change. That's a common expression that's used to describe the slope, because it's the rate at which the line is changing. And a line, being straight, will have a constant rate of change throughout. That's what allows us to graph them in this way. Okay? So just to show you an example of something in slope-intercept form and how you would graph it, again, this should be very straightforward from Algebra 1. If I have y equals 1/2 x minus 3. All right. You would look and see that that matches something exactly in slope-intercept form. So this is the slope of 1/2, and this is the y-intercept. Oh, I don't think I said that. Sorry. B is your y-intercept. And the y-intercept is the point at which the graph will cross the y-axis, the point at which the line intersects or hits or crosses the y-axis. All right, so if I have y equals 1/2 x minus 3, what I want to do, typically the strategy, is I want to start at my y-intercept and then count using the slope. So I'm going to start at my y-intercept. There's x, there's y. My y-intercept is at -3 right here, so 0, -3 is where I'm going to begin. And then I'm going to follow my slope, which is rise over run. Up 1, to the right 2. We always count to the right, by the way. Always goes left to right. Up 1, to the right 2. So I'm going to go up 1, to the right 2, put a point there. I'm going to continue counting from the most recent point and go up 1, to the right 2, because you can picture that this would make a straight line, right? And you can do that as many times as you see fit, up 1 and to the right 2. If you want to extend the line in reverse, suppose we want to extend it more in this direction, well, just follow the line. Instead of going up 1 and to the right 2, I'm going to proceed down 1 and to the left 2. Because you see how that would keep that same line shape, right? Down 1 to the left 2. Okay? And we can connect all those values together, all those little points, and we make our one continuous line. So that right there is the graph of y equals 1/2 x minus 3. All right. So let me show you another example. Suppose we have y equals negative 3x plus 4. Okay. Again, there's something in y equals mx plus b form. I'm going to start by drawing my coordinate plane here. I identify my y-intercept. My y-intercept will be at 0, 4. That's going to be 1, 2, 3, 4 right there. Now my slope of negative 3, really, if you notice slope is written as rise over run, we can write, if you feel comfortable, you can write negative 3 as negative 3 over 1, because any whole number can be expressed as a fraction over 1. And this means that our slope is to go down 3, down because it's negative, down 3, and to the right 1. We always go to the right one. Some students think, oh, because it's negative, you go to the left. We never go to the left. Whenever you count slope, you always go to the right. The negative is just what tells you if you're going up or down from a previous point. So here I'd start at 0, 4, and I'd proceed down 3 to the right 1. Down 3 to the right 1. And if you wanted to extend in the other direction, just to continue the line this way, for example, I would go up 3, left 1. And you would see that if you link all these together, it creates a line. Okay? Oh, excuse me. Any questions about that? Hopefully we're good. All right, there's our x. There's our y. So that's how you graph something in slope-intercept form. All right? Let me just ask you really quickly about the domain and the range of these graphs. We're going to take a look at more characteristics tomorrow, but we can certainly start out with the domain and the range. Of this first graph that we did, y equals 1/2 x minus 3, what would its domain be? Well, we'd ask ourselves, how far to the left does the graph extend, and how far to the right does the graph extend? Being that it's a line, it extends infinitely in both directions, correct? So I would say that our domain is negative infinity to infinity, hence the arrows on either side. And the range, yeah, that's also negative infinity to infinity, right? Because if you notice, it's extending forever to the left, forever down, and forever up, right? No matter if the line is tilted this way or this way, the domain and range of any linear function, as long as its slope is not 0, is all real numbers. Always, always, all the time. The same thing is true here. Notice this is a positive slope, this is a negative slope, but even our negatively sloped line is still extending forever to the left and right, going forever left, going forever right, so our domain is still all real numbers, and it's going forever down and forever up, so our range is still all real numbers. Okay? So again, for any linear function, as long as the slope is not 0, it will have a domain and range of all real numbers. Okay? So that being said, that takes care of slope-intercept form. Another way that you might see these graphs presented to you is what's called standard form. Okay? And standard form looks like this. Looks like ax plus by is equal to c. Some number times x plus some number times y is equal to c. And although standard form, admittedly, I think is a little less useful for graphing, it's definitely useful for word problems. And a lot of word problems translate very directly to standard form versus slope-intercept form. So that's why standard form is useful. It comes up in applications a lot more. All right, so how do we graph something in standard form? Let's take a look at an example. I have 2x plus 3y is equal to 6. It's still going to make a line. It's still going to graph to a regular old line. But how do we graph something in standard form? Well, the very first thing we could do is we could take this and convert it to slope-intercept form. Right? one thing that we can do is we can use a little bit of algebra to manipulate that and get it to be slope-intercept form. So how would I do that? Well, I want this to look like y equals mx plus b, right? So I would need to move the x on the other side. I could take this equation and subtract 2x from both sides. That gives me 3y is equal to negative 2x plus 6. And you may notice that I opted to write this as negative 2x plus 6 as opposed to 6 minus 2x because I know I'm going to need it in this order. I'd like to have it in that order to be a little more comfortable. So that's why I wrote it as negative 2x plus 6. And then I can divide 3 on both sides to get y by itself because I don't want 3y equals. I want 1y, regular old y equals. That gives me y equals negative 2/3 x plus 2. And now I can go from there. I can graph it just like I graph my slope-intercept form, where I have my y-intercept at 2. I'll do it actually up here in blue. I have my y-intercept at 2. I would go down 2 to the right 3, down 2 to the right 1, 2, 3, down 2 to the right 1, 2, 3. And if you wanted to extend it in the other direction, I could go up 2 and to the left 3 because it keeps following that same pattern and connect those all together. And I get my lovely line. This one in particular is the negative 2/3 x plus 2. So that's certainly one way that you could go about it. You can convert it to slope-intercept form. All right. Another way that you could go about it, and I think this is especially useful for standard form, is you can find your x and y intercepts. In other words, if you find the point at which the line intersects the x-axis and you find the point at which the line intersects the y-axis, you can then connect those two together and that will create your line. In order to find the x-intercept of a function, the x-intercept means that you are sitting exactly directly on the x-axis, correct? So in order to find the point where you're sitting on the x-axis, plug in 0 for y, because any point on the x-axis would have 0 as its y-coordinate, right? Because you're sitting right on the x-axis. You're not going up or down anywhere. You're exactly neutral. So if you plug in or substitute 0 for y, that will tell you the point at which you're on the x-axis. So that's exactly what we can do. We could take our 2x plus 3y equals 6. I can plug in 0 for y, so that will say our x-intercept would look like 2x plus 3 times 0 is equal to 6. And now I could just solve for x. 3 times 0 is 0, so I get 2x is equal to 6. And dividing both sides by 2, you would find that your x-intercept is at 3. Right, so since we got x equals 0, that means that our x-intercept is at the coordinate 3, 0. You can notice that that's consistent with the graph that we drew up here as well. Right, notice our x-intercept is right here at 3, 0. Right, that's our x-intercept. Okay, to find the y-intercept, kind of works in the same way, where if we're sitting on the y-axis, then our x-coordinate would be 0, right? Because we would not have moved anywhere horizontally. We'd be sitting right on that y-axis. So for this one, we plug in 0 for x. Okay, and I'm getting to the bottom of my page here, but if I do that, I'm going to take my 2x plus 3y equals 6. I'm going to plug in 0 for x, so that gives me 2 times 0 plus 3y equals 6. And a little bit of algebra 1 here. 2 times 0 is 0, so you get 3y equals 6, which results in an answer of y equals 2 if you divide by 3 on both sides. Y equals 2 means that your y-intercept is at 0, 2. Okay? Once again, that's consistent with our function up here. This is our y-intercept of 0, 2. And we saw that that was the case as well when we actually converted this to slope-intercept form. So, two strategies that you can use for dealing with any graph in any linear function in standard form. Number one, you can convert it to slope-intercept form and just go with our usual y equals mx plus b approach. Or you can find the x and y intercepts by plugging in 0 for y, plug in 0 for x. That gives you the x and y intercept respectively. put them on the graph, and then just connect them to form that line. Because really, you need 2 points to form a line, and no more than that, right? Because if you just connect them and then extend, you have your line. All right. I want to note very quickly that you can certainly use the x and y intercept approach with slope-intercept form. A lot of time, I personally think it's a little overkill, but there's nothing stopping you from taking something like this, y equals negative 3x plus 4, and saying, what's the x-intercept? Well, let's plug in 0 for y and find out. What's the y-intercept? Let's plug in 0 for x and find out. In fact, if we do, you'll notice it'll be consistent over here, right? If I find the x-intercept of this graph, for example, y equals negative 3x plus 4, I'll plug in 0 for y. And if you notice, I would get 0 is equal to negative 3x plus 4. If you subtract 4 from both sides, you get negative 4 equals negative 3x. Divide both sides by 3, you'd get x is 4/3, about 1 1/3. And if you notice with my line, I wasn't super exact, but it does cross the x-axis a little bit past 1. And if I was being very exact, that would in fact be at 4/3, comma 0, or 1 1/3, comma 0. And then to find our y-intercept, we would plug in 0 for x. If I did that up here, that would actually be really fast, because if you notice in any slope-intercept form, that's why this is the y-intercept, because if you plug in 0 for x, you literally just are left with that, right? You would get y equals 4. Y equals 0 plus 4. Y equals 4. So that's why in slope-intercept form, this is the y-intercept, because if you plug in 0 for x, that's all that's left over. There's no other choice. And we saw that was consistent in the graph that we just did, right? Cool. All right. So any question about standard form or slope-intercept form, please let me know, but try to digest that a little bit. But one other thing that we can do with our linear functions is not just like approach something in slope-intercept form or approach something in standard form. What if it's just something in some random form? Does that mean like we have to cry and give up? No. It means that we could just try to convert it to one of these. All right. So what if something is in a random form? All right. So I'll say, well, what if it's just a random form? Okay. For example, what if you have something like this? 3y minus 1 is equal to 2 times x minus 4 minus 1 plus 4x. Holy cow. Does that mean, again, does it mean we cry and give up and complain? No. We could just do a little bit of algebra to get to something that's familiar. We can either convert it to standard form or convert it to slope-intercept form. Personally, I think slope-intercept form is easier to graph with, so I'm going to opt to convert to y equals mx plus b. But you can convert to standard form if you really want to, convert to ax plus by equals c, and graph from there. So what I'm going to do is I'm going to use algebra to convert to my y equals mx plus b, which is, again, your slope-intercept form. Again, I don't want to dissuade you. If you're really attached to standard form, you certainly can convert to standard form. If you're really attached to your x and y intercepts, you can do that as well. Plug in 0 for x, you'll get your y-intercept. A little bit of algebra, but you'll get it. Plug in 0 for y, you can get your x-intercept. You can solve for that. But I'll just convert it to y equals mx plus b here. In order to do that, I want to clean up the right side a little bit. I'm going to leave this 3y minus 1 for now. Cleaning this up, we'll do a little bit of distributing there. We'll get 2x minus 8, 2 times negative 4, minus 1 plus 4x. Now we can combine like terms on the right side. Again, I'm going to leave the 3y minus 1 for now. Combining like terms here, I would get 2x plus 4x is 6x. Negative 8 minus 1, negative 9. Okay, does everybody see that? Does everybody see that? Now I can go forward from there. If I add 1 to both sides, I get 3y equals 6x minus 8. And lastly, I can divide both sides by 3. Divide by 3. Divide by 3. And that would give me y is equal to 2x minus 8/3, which is 2 2/3, right? If you prefer, 2 2/3, or 2.6 repeating, negative. So that would mean you just start at that value of negative 2 2/3, which, just because it's a fraction doesn't mean we have to be afraid of it. We can start at that value, and then we would go up to over 1. Okay? What if, just for the sake of simplicity, because I'm thinking maybe working with a fraction is a little tough for the first example, what if instead of that, I had that this was a minus 2 here, and that's a minus 2? If that's a minus 2, then we would get negative 10 here, if you notice. And if I did negative 10 plus 1, I'd get negative 9. So just to show you, what if I had 3y minus 1 equals 6x minus 10? Now I would get 3y equals 6x minus 9. Divide both sides by 3, you'd get y equals 2x minus 3. That might be a little easier to visualize, right? Versus dealing with a fraction at the very first glance. So if I have that, now I can go ahead and say, oh, well, my y-intercept is at negative 3. My slope is at 2. So the way that I would graph that, just to show you really fast, in the middle of the page here, is I would start at my y-intercept of negative 3, right? Because my y-intercept is going to be 0, negative 3. And I'll follow my slope of up 2 over 1. I'd go up 2 over 1, up 2 over 1. And it would look like this. Okay. Notice if we dealt with the fraction, it doesn't mean that it's scary or impossible or we have to abandon all hope. It just means that we deal with it. Negative 2 2/3 is negative 2 2/3. I'll say it's right about there for our y-intercept. Right? It's not quite at negative 3. It's a little above. And then from there, I'm just going to follow my slope again of 2 over 1. And I'll go up 2 spaces over 1. It should be approximately there. Up 2 spaces over 1 would be approximately there. And then I just connect them all together. And even though it's not exactly an integer, like it's not right on the grid, what would we call the lattice point, but even though it's not exactly on the grid, it doesn't mean that it's impossible. We can still approach those fractions as well. And if you notice, just to hammer this point home one more time, my domain and my range would be negative infinity to infinity for both, right? Because they would be extending forever left and right. They'd be extending forever bottom to top. Okay? See, fractions are your friends, not food. No reason to be afraid of them. Any questions about that? Hopefully we're good. I'll do one more example of graphing a linear function in a random form. Let's get to it in my notebook here. And then we'll call it a day. All right? So how about something like this? Ready? And these are fun because they can involve a lot of algebraic steps. So it's pretty good time. How about, let's do this one. We have negative 3 times x plus y plus, I just want to make sure I'm reading this correctly, plus y minus 1 is equal to 5 plus 3x. Okay, what if I had that? What if I had that? So if I had that problem, what I would do is, again, a little bit of algebra to make life easy for me. I want to try to get it to look like y equals mx plus b. So I'm going to take this negative 3 and distribute it, giving me negative 3x minus 3y plus y minus 1 is equal to 5 plus 3x. We can combine all those like terms on the left-hand side of the equation, That gives me, looks like right here, negative 3y plus y is negative 2y. So that's negative 3x minus 2y minus 1 is equal to 5 plus 3x. Now I know I want it to look like y equals mx plus b. So we need the y by itself on the left-hand side. Let's get everything else to move over to the right. So in one fell swoop, I'm going to add 3x to both sides. I'm also going to add 1 to both sides to undo those. That gives me negative 2y is equal to, let's see, 3x plus 3x is 6x. 5 plus 1 plus 6. Notice how I opted to switch those around to write the x first, because I want it to look like my familiar slope-intercept form of y equals mx plus b. Last but not least, I'm going to get y by itself by dividing both sides by -2. And remember, I have to divide every term by -2 when I do that. Just like I did up here, I divided everything by 3. Here, you divide everything by 3. You get y equals -3x minus 3. Okay? Now we're in our happy place. Now that's a nice line that we can go ahead and graph in slope-intercept form. I'll do that for you really fast. Here's our line here. Oh, not my best work there. We got y-intercept of -3 right here, right? Because that would be our y-intercept in slope-intercept form of 0, -3. And now I follow my slope of -3 over 1. So from there, I'm going to go down 3 to the right 1, down 3 to the right 1, getting pretty low here. And if I want to extend it in the opposite direction as well, I can go up 3 and to the left 1, up 3 and to the left 1. Okay? And we'd end up with this graph right here. Alrighty? That's our x and that's our y. Certainly, we can also take something like this and find the x and y intercepts. I encourage you to do that on your own. If you take something that looks like this and find the x-intercepts, just plug in 0 for all the y's, and you should get that the x-intercept is -1 if you solve for x in the algebraic equation that's left. And the y-intercept we saw is -3, but you could find that by plugging in 0 for all the x's, and you would end up with y is -3. Alrighty? So, last note about this one. It should go without saying at this point, but just to make sure, our domain and our range is in fact all real numbers for both, because regardless if it slopes positively or negatively, as long as it's not a slope of 0 would still have domain of all real numbers, notice, because it would still go left and right forever, but its range would only be one specific value, which is actually kind of cool. But the domain here would be -infinity to infinity, and the range would be -infinity to infinity as well. Alrighty? So just a little recap, what we did is I defined a linear function for you. I then presented to you the slope-intercept form of a linear function, talking about slope being rise over run with a y in there. To remind you, it's vertical over horizontal, change in y over change in x. We then define positive, negative slope, and 0 slope. It always goes left to right, so if you're climbing upwards, it's a positive slope. If you're descending downwards, it's a negative slope, and 0 slope means you're staying exactly flat. Anything in slope-intercept form, you can graph it by starting at the y-intercept and following the slope, like this. Starting at the y-intercept and following the slope. Or you can plug in 0 for y and 0 for x to find the x and y intercepts respectively. Same thing with standard form. You can either convert it to slope-intercept form if you so desire by just a little bit of algebraic manipulation, or you can go ahead and find the x and y intercepts by plugging in 0 for x, 0 for y, and there you go. All right. Lastly, we saw that if something is presented to you in a random form means that you can just use a little bit of algebra to get it to look like y equals mx plus b. This one came out as a fraction, but it doesn't mean we have to be all afraid of fractions. You can just approach them normally, where we put the y-intercept here and follow the slope. If just to show you a little more clarity with integers, same thing, y-intercept and follow the slope. And then another example down here of where that exact same thing happened. We converted to y equals mx plus b. I started at my y-intercept at 0, -3. I followed the slope of down 3 over 1, and I end up with my line here. Okay. Likewise, with anything in a random form, you could plug in x and y intercepts and go from there. All right. So that should be a nice little review of graphing linear functions. Again, we're going to tackle all sorts of higher order functions in Algebra 2 CP. Quadratic functions, cubic functions, quartic functions. So linear functions is a nice basis to start out the year to make sure that we all understand this level, because we're only going to continue to build and build on that. If you have any questions, please feel free to reach out and let me know. Please try to complete the practice problems that are attached to this video, because they will really, really help. But other than that, I hope you have a great rest of your day, and I'll see you later. Bye, everyone.